Thanks for everybody joining us today. This is my last session I'm doing for the Data Platform Summit of this year, 2021. You've seen me in various aspects of this event, from keynotes to sit-ups, serverless pools, to managed instance, to a Q&A session today. But hey, I got to admit to you, it's so much fun to go back to my bread and butter every once in a while, and that's some of the internals of SQL Server, and in this particular case, also a little bit of Azure SQL, and that's about memory. So let's do some logistics first before we get going and crank it into this content, because you're going to love this stuff. We got some really deep internals for you today. But I want to catch up real quick and tell you that I'm going to present this in a way hopefully you understand. So it's deep internals. We're going to use the debugger in some cases, but also it's in a way hopefully that you can understand the complexities and the fundamentals of memory, because it's a very, very important topic. So logistically, look at your screen right here. Bob Ward MS, Bob SQL demos. The deck is already up there, the one I'm doing right now. The demos, anything I'm doing right now, demos are in a GitHub repo. You can probably also find this session recorded, some variation of this session from some previous things on the internet. I don't, off the top of my head, know that. But I did update this and make sure that I covered all the appropriate topics today for SQL Server, for Linux, and for Azure SQL. Also, you're going to have some questions. So what I'll do is I'll periodically hover my mouse here and look to see at the chat to see if there's questions in the chat window. Probably do that, right after one of our demonstrations. Another demo. I've got two demos, fairly lengthy demos to show you. And at the end of our session, we have a lot of time. So we'll make sure to address as many questions certainly as we can. So what the heck are we talking about memory for? In my career at Microsoft, I think it's 28 years, I've lost count. Using SQL Server, perhaps memory has been one of the most least understood concepts of SQL Server, and it's not your fault, it's our fault. We built a fairly complex memory management system within the SQL Server engine on purpose. We did it because this is a database engine that's very robust. It needs to handle the workload needs of many different variations, many different platforms, many different environments. So we ensured that we built the right foundation, and we take advantage of operating system primitives to provide a very dynamic system, and a system that, again, can adjust and adapt to many different scenarios. So let's get into our content. What we're going to do is today, we're going to talk about a little bit some architecture. We're going to talk about configuration choices you make that affect how the architecture behaves, and a little bit about what I call accounting, like how do you look at some of the numbers and what do they mean? We'll certainly look at dynamic memory management, because you need to understand a little bit about how does SQL Server behave as memory needs fluctuate and as pressure occurs within maybe external things going on within the system and internal things within SQL Server. There's some other memory topics to cover, things like plan cache and so forth. And then we want to certainly talk about SQL Server on Linux. What are some differences there, containers and Kubernetes? It's not a lot of differences, but we want to kind of cover some of that. And then finally, I've added to this presentation from past ones a little bit about Azure SQL. How do we treat memory for platform as a service for the SQL Server engine and the Azure SQL environment? So with that in mind, let's start out by talking about the architecture at the highest level. This is Bob's view of the world of memory architecture. If you look at the SQL Server process, at a highest level, you can think of memory that the SQL Server engine manages and memory outside of what we manage to look like the following. One is we have caches. Okay, you're used to the buffer pool or B pool. This is where all the database and index pages are stored. It's the largest cache we have. We have a plan cache for queries and procedure plans. We have other caches and pools that we build and we use for other mechanisms. And then we have column store, which is a separate type of cache we use for indexes, for column store indexes. Now, why are they called caches? It's because a cache within the SQL Server system can grow, it can shrink, and it has something called a backing store. Just like virtual memory happens in an operating system, the backing store is the page file. So the backing store for the buffer pool is what? It's the database files for your database pages. The plan cache backing store, by the way, turns out it's system table storing stored procedure code, or it's your application with your query text. And then other caches and pools may or may not necessarily have a backing store. They don't always need that, but in some cases they do. And then column store, people always think of column store as an in-memory technology. And certainly it is true that column store is most efficient when it can be compressed and fit into memory, but it doesn't have to be actually. So column store indexes, of course, are backed by the index structures that store the column store. Now, there's something called fixed memory within SQL Server. Notice it's a lot less in this diagram. It's a smaller block. And why is it called fixed? Well, we can grow and shrink this when it's not being used. We use something often called a memory object for this fixed memory, but there is no backing store for fixed memory. So when this memory is in need and in use, let's take an example, connection memory. You start connecting to SQL Server, a bunch of connections come through. We allocate memory with a concept called a memory object, think of like a heap, to store information about your connection. It may not be big, but we do that. That memory is fixed. We can't page out your connection structure about your memory, right? So it's a fixed amount of memory, and connections and memory grants being examples of those. The reason why this is significant is we're going to talk about how dynamic memory management works. We can never shrink the fixed memory when it's in use. Okay, so if SQL Server does everything it can based on pressure to shrink its caches, and memory that's being used and fixed can't be shrunk, you might run out of memory within SQL Server. And so there's some examples that you can easily cause those type of scenarios. If you set the max server memory of SQL too low, it's going to cause us to shrink everything and cause this problem. So you have cache examples and you have fixed memory. Notice again, though, that the fixed memory is typically not a lot compared to the caches. That makes sense, right? You want your caches to be robust. Now, another example of memory that we have is SQL Server overhead. This is memory not managed by the SQL Server engine. What is an example of that? A thread stack. So when a thread is created, whether it be on SQL Server on Windows or SQL Server on Linux, doesn't really matter. There is a portion of fixed memory allocated to store memory for the stack of a thread for call stacks information. That's fixed. We cannot shrink that. In addition, you'll find out when we start talking about the concept of locked pages, that memory is not locked. SQL Server can only lock what you see in the diagram that it manages, which is the blue squares and the gray. Now, one other memory management piece of the architecture, notice it's fairly larger in size, is Hackathon in memory OLTP. It doesn't have to be that big, but when people like to use memory OLTP, they usually like to use it, of course, to store data, so it can grow quite large. Now, it is fixed. What does that mean it's fixed? Well, it means that the only way to shrink this memory is to delete data, because remember, the whole idea is it's in memory. So we cannot, during any kind of pressure, shrink this memory if it's all being used by actual data. When you delete rows, that's when we can go and do cleanup and reduce the amount we need. And notice also that doesn't take up the whole box. If you look at things like fixed memory, or even other caches and pools, or plan cache, or buffer pool, none of these can take over the entire memory of SQL Server. There is management within the system to make sure that doesn't happen. Okay, that is kind of a look at the entire view of memory architecture, except for one other piece, and that is a memory clerk. And I only bring that up because that term is going to come up when we look at accounting. What is a memory clerk? It's a type of memory that SQL is managing. So for example, the buffer pools, it turns out, is the name of a clerk. We account for memory by clerks. The plan cache has a couple of different names for a clerk. Hackathon has a clerk. Other caches have these clerk names. So column store does. So when you go through and look at the overall memory management of SQL and what is consuming the most memory, again, for what we're managing, you look at it in terms of clerks. And we'll show you an example in our accounting section of what that looks like. Okay, with this in mind, keep mind of the concept of paging and SQL Server. So I'm going to spend a lot of time probably repeating myself on the same thing. Why am I doing that? Because these questions continue to come up time and time again about how this works. I don't blame you. It's a complicated topic. So number one, we kind of alluded to this already. And the reason that's why I call it all the caching. SQL Server can do its own paging based on memory needs. The buffer pool, we can write pages of the buffer pool if they're changed to database files. If they haven't changed, we could just free up the memory, okay? The plan cache, we can free up these pages and we don't have to write them anywhere. We just have to reload them from system tables. So that's kind of a paging concept. But again, some memory is never pageable, like connection memory. We don't have a file laying around to say, oh, flush out the connection structure to disk and then bring it back in when you need it. Windows as an operating system, the same thing applies to Linux, can page out process memory. Now, in terms of Windows, this is specific to Windows because Linux will mention a little bit of differences there. They don't have this concept of working set trim. They do something different, but some of these concepts will apply. So what happens is when the Windows operating system decides to page out memory of a process like SQL Server, it can write out those pages in terms of Windows pages. It doesn't know anything about SQL database pages to a page file. We call that process a working set trim. Now, why could that be a problem for those of you that use SQL Server? It's because when Windows does this, SQL still thinks it's in RAM. We have not done our paging here. Windows has paged our memory. It could be any of these things I list on the architecture screen. We think it's all still in RAM. We're just kind of chunking along. And it could even be thread stacks. Now you can see this visible problem if this occurs by looking at these performance monitor counters to see this working set trim scenario. So why am I telling you that? Because when we start talking about the word locked, keep in mind what I just said about Windows paging out process memory. Okay. You're going to make configuration decisions for SQL Server that are going to affect the behavior of some of this paging that occurs and how we manage memory. So number one, there's something called a memory model. This is not an option you pick at setup with like a checkbox. The default is called the conventional memory model. That's the default behavior of SQL Server when you install it. We are going to use the virtual alloc APIs from Windows to make that work. Now, there is another model called locked pages. Now, that is a SQL Server term, okay, locked pages. And again, there's no button you click. What happens is, if you're using Standard or Enterprise Edition, and the locked pages in memory privilege for the process, for the account of SQL Server is set, we, by default, when we start up SQL Server, we'll go use what's called the Address Windows Extension APIs in the Windows API set to allocate much of the memory you saw in that architecture screen, okay? That's going to become significant when I talk about trimming in a second. Large pages is the third option of this model. When you use traceflag 834 with SQL Server, we will allocate memory up front for max server memory, okay? When you do that, we will use the virtual alloc API with an option called mem large pages. And the reason that is done is because it can be more efficient in some scenarios. Now, a couple notes here. Traceflag 876 is to be used instead if you're going to use column store with large pages. If you want to use column store with large pages, you would want to use this traceflag because we've seen issues with 834 if you're using column store. And almost no one really does this actually in practical scenarios. We use this in benchmarking, and it is true that in big warehouse scenarios, this can be more efficient for to use. But look at that allocate up front option there. If you do a failover for a cluster instance and we got to start up SQL Server, get ready. We have to allocate the memory up front, so it takes longer to do that. So large pages, I would say, is something that should only be tested by customers and decide, can it really benefit your workload? But I would say locked pages is something I recommend almost anyone use. There's very few scenarios where I don't think it makes sense to use that. Okay. What about max server memory as a configuration option? Very controversial, I know. And many customers still use 0, which means auto. Auto does not mean use every byte and bit of the physical memory of the machine. What it means is that calculation, the minimum of almost all of RAM or 50% of available RAM. Okay, and that's because of the fact that maybe you have had memory pressure in your system. So it is auto and it adjusts. And here's the most important point. Max server memory means this is the ceiling to which SQL will never grow above. We call that the target. It does not mean that we've allocated that memory yet. It just means that's our goal to grow to. We may never grow to that depending on pressure, but we'll never grow above that ceiling. Now, many choose on very large server systems for this to not be 0 and less than physical RAM, especially if you're using locked pages. I'm sure you're asking yourself, well, what should I use? We've got a nice knowledge base article that talks about this. It varies, unfortunately, a little bit on how you should do that, but many choose to do this because they found if they leave it at 0 and use locked pages, sometimes Windows does not behave great when you've used almost 95% of physical RAM. So an important term here, external pressure, which is operating system pressure outside the SQL process, may cause us to lower our ceiling dynamically, but it doesn't change your configuration value because we could go back up to what that value was if we determine the pressure is gone. Okay, Min server memory is the floor. So max server memory, the ceiling, min, the floor. So we're going to dynamically grow within this range. This is the floor to which SQL will not shrink below. And we don't allocate this at startup as a minimum. Don't think in terms of like, well, I'm going to allocate this up front to get going. Remember, large pages, we're going to allocate max server memory up front. For min server memory, though, we do not allocate it up front. What happens is SQL will start growing. And if we, for some reason, have pressure and have to lower down, we will never lower down below that ceiling. So why would you even use these things? Well, a lot of times in multi-instance scenarios is when you want to start playing with, should I use and play with these compared to other instances? Because guess what? Instances don't talk to each other when it comes to memory management on the same virtual machine or computer. Oh, there we go. Multi-instance configurations, they don't talk to each other. They don't say, oh, you're at max server memory this and I'm max server this. Let's go all make sure we coordinate each other. That's up to you to figure out how to go do that. This is why some people do actually set min server memory in scenarios where they want to make sure in multi-instance, they don't have SQL ever go below a certain value. Okay, now that you've had that context in mind, what does locked really mean with SQL Server? So first of all, locking memory allocation for SQL Server means I want to make sure Windows won't trim the working set. Remember we talked about trimming the working set. Windows taking the memory of a process, writing to the page file, which is going to be slower to access that memory, and SQL doesn't know it. Remember we talked about if you're running standard or enterprise and you've got this privilege set for the account associated with SQL Server, like the service account, then SQL, when it detects this, will start up and start using this locked model. Not part of the working set is the magic of why it can't be trimmed. It turns out, if we use the address Windows extension APIs, which by the way, you can go look that up if you'd like, it was really written for 32-bit systems way back in the day. Turns out if we use these APIs to allocate our memory, most of our memory, it is not part of the working set of the SQL process, and therefore Windows never sees it. I'll show you an example of what that actually looks like. Other memory, though, is part of the working set, like stacks and heaps and so forth, and they can be trimmed. Large pages also requires this privilege, so it is also locked. Now, one little caveat and note there. As it turns out, even in the conventional memory model, we can use some locked pages memory if this privilege is set and standard addition is detected. The only time that would ever occur is a trace flag, which I'm going to show you for demonstration purposes, because as it turns out, if the privilege isn't set, we don't use the lock model and we can't even lock anything because we don't have that privilege set. In other words, to use the AW APIs as a programmer, you must have those privilege set to do it. And therefore, this last point, you only see this in some of the demos I'm showing you, but it's not normal in production. Okay, what about SQL locking memory? What does that even mean? So independent of the lock page model, just forget about what model you're using. Max server memory is a ceiling where we won't grow, but min is the floor we won't go below. So min is a way you can lock SQL's memory within the SQL memory management system. If you set min to max, which again, I don't recommend necessarily doing this unless you make sure you know what you're doing. If you set max to 5 gigabytes, 20 gigabytes, and min to 20 gigabytes, SQL will grow to 20 gig and it will never shrink below 20 gig. In a way, you've locked in SQL Server from paging its own memory. Windows has no idea about this thing. This is independent of a working set trim or anything. This is SQL having the ability to not trim its own memory. We call the behavior of SQL trimming its own memory internal pressure. And internal pressure occurs because we've hit that ceiling and we need, people still want to allocate more memory, and we have to start playing around with what do we start trimming to make sure we can not grow above the ceiling. That's the idea of internal pressure. We'll see a diagram in a second that'll help explain that. Actually, we'll see it now. So if you look at this Perfmon image right here, I took a snapshot of this, and we're going to show you this live in a demo in a second. You'll notice here that I have a target, a total, and a private bytes. And you'll see here that the red line represents the ceiling, okay, the ceiling. In fact, let's just do the animation here. The total server memory right after startup, this is how much memory SQL is consuming. That counter is a SQL counter, not a Windows counter, not a task manager counter. Private bytes is the Windows counter. So notice here the black line that's highlighted, which is green, represent the amount of memory SQL has allocated right after startup, which is in this case like 500 megabytes, okay? Notice here that the ceiling or the max server memory, we call that the target, is up to the red line. So This is the amount we can grow to. We can grow between that total and up to the red line and no more past that red line as we're using SQL Server, okay? In this particular case for 1 GB, that could be somewhat the physical amount of RAM on my system, or I could have fixed that ceiling because I actually used a max server memory counter. Okay, now let's say in this example, a query starts loading buffer pool cache pages because pages that it needs are not on disk. What does the behavior look like? Notice here that the black line starts going up towards the red line. So when we get almost right to that red line, the query could still be running, but now we have hit the ceiling. We don't go all the way right to that ceiling, we go very close to it, okay? And now what will trigger if the query still needs database pages to be brought into cache is called internal pressure. What do I mean by that? I mean, SQL Server manages its own memory, so it has resource monitor looking at this thing going, hey, we're almost at our ceiling here, but we need more memory. What are we going to do? Well, somebody else has to give up their memory for us to use the memory we need. So that's where you'll see maybe the buffer pool cache freeing up some pages, writing out dirty pages. Plan cache can start being trimmed. The different caches can start being managed to say, you need to give up some memory because somebody needs memory for the buffer pool to bring in pages. Because remember, we just can't keep growing past that red line. Funny story. First started working at Microsoft years ago. SQL NT first coming out. This system, this dynamic memory system has been around for a while. I love my counterparts in the Windows support team, but they early on used to come to us. They were not used to seeing SQL Server cases and say, hey, what? You guys are leaking memory. You've got a memory leak. This SQL process, every call that comes in is a memory leak. And I'm like, well, show me the Perfmon chart. It would look like this. And I'm like, no, do you see it flattening out right there? And they were like, yeah, because they're looking at this private bytes counter here, this blue line. I said, you see the blue line flattening? Yeah, we don't understand it. Why is it flattened? You know, we're like, that's because we're dynamically growing and we're getting to a point to where we hit our ceiling and then we start leveling off. So they would look at this blue line right here, up here as a leak of memory. And I'm like, no. If that blue line just keeps going and going and going and going, and I showed them how to use the SQL counters, notice that the blue line is slightly above, I'll go back here, the blue line is slightly above the black line here, or the green line. It's always above that because that's some of that memory that's in addition to SQL's memory, like thread stacks and heaps. I said, that blue line is always going to rise until it flattens out because SQL is using much of that memory to allocate for its own caching purposes. And that's a great example of dynamic memory growth of SQL. Okay, let's say external memory pressure kicks in. What do I mean by that? So somebody allocates more memory on your operating system than SQL Server. And so the operating system tells SQL Server, hey, we're low on memory here. And we recognize those scenarios. SQL Server is designed to recognize low memory signals on a Windows system. And it says, oh, I'm going to drop SQL Server memory. That's external memory pressure. But notice here, the black line goes down, but so does the red line. So what we do is we lower the ceiling of SQL Server. We deallocate memory that was already allocated. So we're dropping that ceiling down. And now everybody has to behave within that ceiling, that floor to ceiling concept, right? So that's called external memory pressure. We're dropping the ceiling and then operating now and growing and shrinking within that. Okay, so let's say here a query is still running in this scenario when we drop here. What's going to happen? Well, we're going to sit here and we're going to be dropping pages out of cache, and you might run into something called like page sloshing, right? Because we're having to go grab pages on disk that we already got rid of, again, over and over and over. So it's a very, very bad performance scenario. And then if the query completes, notice here that the red line can go back once the external memory pressure is gone. But notice here that the green line doesn't go back up. That's because in this scenario, the query finished, we haven't asked for any memory. If the query ran again or another query comes in, we would then grow right back up to that run line, which is a great example of dynamic memory management. So you can see here, internal pressure, external pressure, growing, shrinking, and us adjusting depending on what's going on in the system. This is a perfect example of what you might see. And so why is it important to you? This is because when anybody ask me a question about memory management, say, hey, SQL's not allocating enough memory, or SQL has a problem with memory management. I ask two questions. What is the total and what is the target? Every single time I ask them, what are those two numbers? Because it tells me what is the ceiling of SQL Server and what is the floor. And if they say, oh, my max server memory is set to like 1 gig, I'm like, well, it'll never go above 1 gig. And they're like, oh, I didn't know that. So I'll set it to 100 gig. And then they're like, oh, SQL uses all the way to 100 gig, but it doesn't go past that. I'm like, yeah, that's because you said it only can use 100 gig. So target and total are two of the most important counters you'll ever see with SQL Server. And again, the point here about private bytes in this scenario is it will always be slightly higher than that black line. What you're going to find out, depending on the memory model, is what you see in Task Manager could be slightly different, because Task Manager is only going to show you the working set. It's private bytes accounts for memory that is also locked or not part of the working set. This is why it'll always be more accurate of how much memory SQL has allocated as a process for Windows. Okay, so let's look at accounting a little bit, because you're going to be looking at various counters for SQL Server, and you're going to wonder, how do I put all this together? So first of all, Task Manager is something often looked at as a very quick glance of memory. And notice here, I've got the working set counter for SQL Server. DMOS process memory is a DMV that shows you several things. And notice I've actually added some of the counters here to kind of correlate all this together. Okay, so number one, notice that the working set points here to this physical memory in use. Now, in this particular scenario, I'm actually using the locked page model, not the large page model. I know that's confusing. That's because we can actually use large pages in some cases internally, not a lot, not for the buffer pool, for a small amount of memory. So physical memory in use is the combination of our working set, which again could be memory like thread stacks and heaps and so forth, and SQL's locked memory and large memory together. So if you add these up, it roughly accounts for that number. Commit size is actually equivalent to virtual address space committed. So you can kind of look at the counters and kind of put this together to see what it actually looks like. And there's other memory being allocated just as part of a SQL being a process, which is why this right here can be larger than that. Okay, but it's not usually very much larger at all. And again, that's my point about large. It can be used without these trace flags, but it will only be a very small amount in the locked page model. Okay, you ever look at DVCC memory status and wonder, like, what do those numbers mean? So let's equivocate some of this stuff. So number one, notice that locked pages lines up with this DMV, and large pages lines up with this column of this DMV. And then you have OS sysinfo, and you're probably wondering, what are those numbers? Notice here the word target, but also the word committed. How do they line up? Notice here that current committed and memory status lines up with this column, and target lines up here. But what about Perfmon, Bob? Aha, target should be the same as what you see for OS sysinfo and memory status, and committed is total. So when you see the word committed in OS sysinfo, this is why if you put me to a SQL server and I don't have Perfmon, I can look at OS sysinfo and I can tell your total and your target without actually looking at a Perfmon counter, which is a very nice thing to have when you're diagnosing a memory problem with SQL Server. I realize that's fairly complex, but it kind of ties together various ways you might look at the accounting of memory at the highest level of SQL Server. So let's stop and do an interesting demonstration. Okay, this is fairly complex. I've got a little Notepad file. I'm looking at my instructions here because I'm not going to memorize all this. But here's the point I made earlier. This is all in a GitHub repo for you, right? So you can see all of this yourself and try anything I'm trying here. So let's first bring this up. This is going to be our Perfmon. Okay, and notice here, I've got private bytes, I've got total bytes, and target memory all lined up here. And you can see here, I just started SQL Server. So in this case, about 800 meg. I've got target at 17 gig way up here, and private bytes about 1.3 gig. So think about this again. Total, I just started up SQL Server, 800 meg. Target, 17 gig. That's because max server memory is set to 0 in this case. This is like 95%, right, of the physical RAM of my laptop here. And then private bytes is slightly above, which you can't see, the green is like right here, total. Okay, so let's do this. Let's go over and also show you Task Manager. So here's Task Manager. Now I said it was like 800 meg, right, for SQL Server. Notice here that for SQL Server right here, the SQL process here, that it's only about 130 meg as opposed to 800 meg. Why? We're using the locked model. In this particular case, we're using the locked model. And the way you can tell that is you would go into Management Studio, and you can see and run this query right here against OS sysinfo. and I can see how much I've committed, which again is like this 800 meg. Here's a 17 gig, that's the target, and I'm using the locked page model. SQL detects that and tells you, without a look at the error log, what you're using. I can also see here other things in DMVs to find out. Again, remember that physical memory in use? Combination of working set, which I saw in Task Manager, plus my committed memory, plus it's my large, plus my locked. You can see the breakdown of the 800 meg here, right? Plus the working set together, and then I see my total committed. And then I told you about clerks. This is a breakdown of clerks organized by total, the biggest consumers of memory. You see the buffer pool in this particular case is the biggest consumer memory in this scenario. And I've just started up SQL Server. So let's do this. I got max server memory set here to 0. Let's set max server memory to like 5 gig and see what happens. So I'll go over here to Perfmon, and I'm going to look and see what my target does. It was 17 gig, and it doesn't change immediately. Why doesn't it change immediately? The reason it doesn't change immediately is because Lazy Writer is the one responsible for monitoring a change. Now you can see here that this has changed. Notice that the ceiling right here, the ceiling right here is lowered. And it's lowered to be what? Around like 5 gig. Now, our private bytes is still 1.3 gig, and our total is still 800 meg. We are still not grown to our ceiling, but let's go see what that looks like. Let's go run a query in Management Studio here. Let's see, I've got one here. Now, if you didn't know who the Baylor Bears are, by the way, I'm such a sports nut. Baylor is the university. I went to school here in Texas, Waco, Texas. They won the national championship in basketball. That's back in April, but I keep talking about every time I remind somebody, hey, did you know we're the national champions? So that's the name of my database. And I'm going to run a query against a table that's got a lot of data. So I'm going to kick this off and go back to Perfmon and look at that. Oh, this is some interesting behavior. You'll see here that total memory here, which is this green line, is actually almost on top of this. You'll see private bytes here in purple, and you'll see the target. Oh, what happened to my total here? So the total, I don't know why the total isn't showing here. Let me go break it down here. Oops, we should see that green. Oh, it's not checked. There we go. I unchecked it. Okay, so it looks like the green line is almost right on top of the red line. It's not actually right at that level, but it's very close to it. In fact, look at these numbers. Here's total at 4.909 and target just slightly above it, right? So we've gone right up to that ceiling, but private bytes is just a little bit over what we've done. Again, that's that fixed memory we actually talked about. Okay, so that's interesting. Let's look at that checked, right? We're still chugging along here. What about, and again, the green line is right on top of the red line. You can't tell there. What about if we lowered the ceiling artificially? And how do we do that? We're going to lower it to 1 gig. So let's do that and see what happens. This is me inducing internal pressure, but in a way, I'm simulating external pressure. Does that make sense? I'm lowering that red line, and notice the purple line and the green line itself. You can't see it right there, but the green line is right there on top of it. Everything gets lowered. So we deallocate memory, we lower our target on our ceiling, and now we have to play within that boundary, okay? Now let's do this. Let's go back and adjust the ceiling back to 5 gig and see what happens. So this is me simulating external pressure is gone, and you should see the red line go back up now to where it was at like 5 gig. Again, the delay is because we have a background process monitoring changes for that. Now we see the behavior. Look here, the green line is still here. We're not going to shrink any more memory we've allocated because we've already done that, but the red line is here. And so you see the green line doesn't go back to the red because we haven't allocated anything yet. But if I go run a query, I'll see it. If I go run this query again, I'll just kick it in again, you'll see it start growing in the model. You see the green growing right up to the ceiling again. So great example of the behavior of dynamic management management and why when you look at these counters, you can understand the behavior. So again, let's summarize what's going on here. Ceiling is max server memory. Total is what we've allocated. I didn't use min here. I didn't use a floor. We grow near the ceiling. We never exceed it. For SQL Server, private bytes will be slightly above it because that's fixed memory. Notice here again in Task Manager, see here, notice that Task Manager is not very high. It's only 93 meg because we're using locked pages here. The working set is not, most of the working set of SQL is not visible to the operating system, so I can't trim it, right? And if we get external pressure or we induce it with max server memory, we lower our ceiling, we run within that. So again, I look at target and totals, ceilings, allocated behavior, task. I look at a combination of these things to understand your memory behavior and why you think it may or may not be happening. I had several people contact me and say, hey, SQL's not allocating enough memory in this machine. And I go right to what the target is. What is your target? They're like, oh, well, this target says it's like, 100 gig and I've got a terabyte on here. And I'm like, do you have max server memory set? No, I don't. Ah, you must have external memory pressure going on in your machine. And then they go look at all the processes running in there and find out, sure enough, there's some other process chewing up all the memory, causing SQL to have to dynamically adjust what's going on. Okay, so that is an example. Let's flip our demo here a little bit and do some debugging. And what do I mean by that? Okay, so what I'm going to do is I'm going to restart SQL Server here. I'm going to stop it. Okay, and I'm going to show you the differences about what some of the debugging options look like. So let's go start SQL Server. Okay, I'm just starting up the process itself. And this syntax that I'm about to use here is in the GitHub repo. So if you're like, Bob, I didn't catch that debugger command you used. What did you do there? So let's start the debugger and bring it over here. And so what I've done is I've attached the SQL process running the lock page model. But SQL has just started up to that 800 meg level again. And what I'm going to do is I'm going to set a breakpoint on this symbol, and I'll explain why. So I'm going to go here. That is a breakpoint at a function call within Windows at kernel base to allocate AWE memory. So if I hit go here, it's like, well, I already hit a hit. What is this? If I hit K to look at a call stack, let's just look at it. So if I look here what's going on at this layers here, I can see here that SQL Server is doing something in its code, and it looks like it's doing something with Hackathon, HK engine. Notice here that Hackathon has its own routine to allocate memory. Everything is going to break down in the SQL engine to the SQL OS part of our system and the operating system. So you can see here that what's happening is that SQL OS within its layers, I'll do this again here, it's making a series of calls, get the right key here, to allocate memory. And it gets to the lowest level and says, I need memory, but I'm using the lock page model, so I'm going to use this Windows API call to allocate memory. Let's hit go again here a couple of times. Yeah, so we don't need any more. Let's go run our query and see what happens. So I'm going to run the query, go back to the debugger, and I hit a breakpoint. Let's go evaluate this compared to a clerk. What is going on here? What is this? Okay, so this is an example of us running a parallel query, and we need a memory object. Memory object like that fixed memory I talked about, and this is a good example of us doing that. And then we come up again to the SQL OS level, and it ends up being the same API call to get that memory. Let's see if we can keep going and catch, let's catch a clerk here. Here we go. I think this is it right here. Nope, that's still a memory object. I wanted you to see the buffer pool. Let's see here. It's always tricky to do this, right? At the right time, because I've got so many things I'm getting here. Okay, let me do this. Let me try this again here. I'm going to detach. I'm going to detach the debugger, and I'm going to restart the server again. I want to get back to the timing of this to show you the buffer pool, so you can see an example of a clerk allocating memory like the buffer pool. So I'm going to stop the SQL process. I'm going to restart it again. Technically can start up the SQL process with the debugger instead of attaching to it, but I'm not going to do that. So I'm going to let the server start up just for a second here. What I'd like to do is get the server started up, like to run a query and show you the buffer pool coming along, like I showed that diagram, needing pages and then using AWE APIs to get it. And then what we're going to do is we're going to compare that to the conventional memory model. So let's attach again with the debugger. Let's go here and set our breakpoint. And let's run our query again and see what happens. Okay, let's run our query. Oh, I didn't set the breakpoint. Well, that causes that. this may not work then. So let's see here. Let's get back here. This is truly hacking, right? We're just going along here. Let's see. I think maybe I was too late to run that. Yeah, so here's a tip. Let's do this. dbcc drop clean buffers. I've already allocated the memory. This is just going to do IO here, so I'm not sure this is going to work or not. Let's see. No, that's just another new operator. Okay, so let's try this one more time. We set the debugger the right way. Stop. Okay, start the debugger. Let it run for a second. We'll try to catch it. It's always a timing thing. You know, there's things I could do. I could try to set a breakpoint like on a buffer pool routine first and then break right after that. In fact, I'm going to probably do that in the conventional model because there are a lot more virtual alloc calls that could happen. But let's try this one more time. I need to properly set my breakpoint. I didn't do that before. I just ran. Okay, so now let's run our query and see if we can catch this thing at just the right time. No, that's still, I'm going to try one more time here, but I don't think I'm going to catch it. Yeah, here we go. Perfect. Hey, here we go, Bob. All right. An example, by the way, just so that you know here, this is the code here to run a parallel query. Okay, this is spawning off of a separate proc to run part of our parallel query. And then if you look here, notice here, bpool read ahead and get from disk. These are calls to go get a page from disk and put it into cache. But as part of this, we're like, oh, we need memory for this. We can't just use memory, existing memory because we don't have enough. So here's that clerk routine I talked about. This is how we track the fact we're using the buffer pool clerk. And then eventually we end up calling the SQL OS routines to get memory. And then finally the AWE routine to go get the memory for the buffer pool. Now remember, once we've populated the buffer pool, we can reuse pages within the buffer pool without deallocating. When would we have to do this again? If we lowered our ceiling. If we had to deallocate memory and grow the buffer pool again. So think of it this way. When we grow SQL's memory and allocate for buffer pool pages, we have to allocate using APIs. Once the buffer pool has been warmed up, we can just share and reuse buffer pool pages, even if SQL pages themselves. Remember, SQL paging is just reusing memory that we have, okay? But trimming with external pressure causes us to deallocate the actual memory in the buffer pool, which would cause us to reallocate when we grow again. This is why pressure in the external case is not a good thing. That's a really bad behavior that can cause all sorts of performance problems. Okay, let's detach and do this a different way. Now I'm going to use an undocumented trace flag. Oh no, Bob, why are you doing that? Because I don't want to go through change the lock memory privilege for my process. So instead, what I'm going to do is this. I'm going to stop the server, and then I'm going to use an undocumented trace flag that forces us to use the conventional memory model. Okay, that's T835. Oops, the SQL. Okay, so we're going to start there. And then what we're going to do is we're going to let the server start up for a second. We're going to go back and we're going to set a breakpoint. But what we're going to do is we're going to set a breakpoint inside SQL OS first, and then we're going to set a breakpoint on the virtual alloc call. The reason is that when you use the conventional memory model, this virtual alloc call happens a lot. So you're not going to catch the behavior you're really looking for. So I'm going to set a breakpoint. And by the way, you're asking yourself, how do you know how to set these breakpoints? You have to know the code. It's the only way to do that. It's not like you could go out and just document, oh, here's the function called to set a breakpoint. So I'm going to do that. Oh man, this is not what I was looking for. We can maybe try to do this now and see what happens. Okay. Here we go. Okay. So this is getting a memory object in this particular case. This is not buffer pool. We won't have to be able to show you that. But what I wanted to show you how virtual alloc is used here. You kind of notice here, this is similar right here to the code we showed you before to allocate with the lock page model. Very similar. This is all SQL code. It's SQL OS code. But the difference is that when we get here to this commit memory block allocator, we use a different call here and a different call here because we recognize we're not using AW APIs. We're using the virtual alloc, which is the conventional memory model. just showing you the differences between the two. And what does that mean? That means any memory in these call stacks can be trimmed in the working set because of the fact we're doing that. In fact, if what I'll do is this, I'll just disable my breakpoint and let this go. Look at Task Manager here. Let's bring that up. Notice in Task Manager for SQL Server, look at how bigger that number is. You see it's like 600 meg. Before it was only like what, 90 meg or something like that. That's because everything SQL is doing is inside its working set now and could be trimmed by the operating system. Okay, so that's some fun demos. Let's get back to the deck a little bit here and keep going to the presentation. Let's do a quick time check here. So I think we've got till 4:15. So we'll kind of keep trucking along and hopefully I'm gonna have some time. But I'll tell you what, let me just look here real quick here in the chat window to see kind of questions. Where should we not use locked pages in memory? I don't know of a scenario where you shouldn't. I think you should always use locked pages in memory. Just use max server memory accordingly, especially in multi-instance scenarios. So that's just a quick answer to that question. And then we'll go back and look to see if we have other questions later in the presentation. Okay, what about some other memory topics that might be important for you? So number one, buffer pool logistics. I still believe, despite some issues that you might run into, that page life expectancy is a good way to look and see how effective is my buffer pool cache and do I need more memory for buffer pool? But keep in mind this, you may not be using buffer pool efficiently. It could be you're putting too many things in cache because you're scanning too much. You're not officially using indexes. So with that aside, that's still a good way to determine, and maybe I don't have enough memory. Maybe I've got external memory pressure causing this. Page IO lash weights are specific to the scenario of what I just showed you. If you have to go read a page from disk, page IO latches are a natural part of doing that. So if you see a lot of those and a lot of wait time on those, you're having to read a lot from disk. And if you see a lot of latency, you've got disk IO problems, try to read pages from disk. And then you saw me do drop clean buffers. Drop clean buffers does not deallocate memory from SQL Server. All it does is go through and say, hey, if there's any buffer pool pages that have not been dirtied or changed, just free those. And again, freeing a page in buffer pool cache, unless there's external memory pressure, we're dropping the ceiling, does not cause it to be deallocated from the operating system. It just means we're marking a page that can be reused for another page. Excuse me. Let's talk just a little bit about NUMA. If you use NUMA systems with SQL Server, we're not going to go to a huge deep dive on that. The goal is to use local nodes, NUMA nodes, when allocating and not balance across nodes. So if a worker thread is running on a given node, we're going to try to allocate on that node. That's because that's the fastest way to get memory in a NUMA system. If you try to go get memory across nodes from the thread you're running on, that's called foreign memory. That's slower. The whole purpose of NUMA is to get that fast localized memory to the bus of where your CPUs are, right? And then some memory, excuse me, that we use, like memory objects, are partitioned across NUMA nodes or even across CPUs to provide efficient memory access. We used to have problems with that in SQL Server in previous versions, but we've kind of created a dynamic system to dynamically partition memory objects when we need to on a scalable basis. Memory grants is a very, very important topic for query performance. And we've done some things you see here at the bottom called memory grant feedback to help you avoid having to worry too much about this. But know this, if you see this come up, a memory grant is fixed memory. Remember the idea of fixed memory, not cached memory? We allocate at the start of query execution, and it's needed to support things like sorts and hashes. If you have not enough memory for the grant, it can result in a spill to tempDB, which is IO, which is slow. If it gets too high, you can see resource semaphore waits or even plan cache eviction because of how much memory you're granted. Memory grant feedback is designed to auto-adjust based on these scenarios. But notice if you run into these things, it's usually an estimation problem going on in your query plan. One important point to note, though, if you want to limit memory grants from causing you problems, you now have the support in SQL 19 to do a value less than 1% of overall memory. That is significant for very large memory systems. The resource governor, APIs, the SQL commands all support doing that. Huge shout out to Andrew Kelly, who pointed out earlier to me that we didn't even have to our documentation actually to state that, which is really a terrible thing on our part. But thanks to Andrew for pointing that out. Andy Kelly, we made those changes and got those in the documentation. Okay, what about memory leaks? Excuse me. Remember our ceiling, our target? You can leak within the target. Excuse me. You can leak within the target And if you see that, you'll see out of memory errors in the error log or message 701. That is leaking within SQL Server's memory management. For example, maybe we're allowing allocation of a memory object for connection memory. The connection goes away, but we forget to free up the memory. It's like a bug in our code. If we did that, what you're going to find typically is that fixed memory we're talking about, that memory will get really big. And you can see the clerks show you information to see which one it might be causing that. That would be like a memory leak within SQL Server. But remember, that's only going to cause pressure within SQL Server, which is why you get these out of memory conditions, because we just can't allocate more memory within our target. If you thought there was an actual leak maybe occurring with external code, like a DLL or something like that that's loaded in SQL, private bytes might be that behavior. If you ever saw private bytes, like in my diagrams, start to really grow above SQL's ceiling, SQL's not the problem there. Our ceiling indicates what we're allocating. Private bytes going above that might indicate some other code in our process space that would be leaking memory. That's a pretty rare condition, but I've seen it in the past. Okay, let's talk about plan cache eviction, a very important concept for performance. So number one, the buffer pool is always going to get more memory. It's a more impacting thing on your application for the buffer pool to not have enough memory, okay? But the plan cache is like one of the other biggest consumers of memory in the system, or it can be, but we limit it because we want to make sure buffer pool has plenty of memory. So we have something called an external clock hand, which you can see through DMVs to see, because anytime we think we're hitting one of these conditions, we've hit the target, we get external pressure coming in the system, or we get like things like large memory grants, we're going to use and move a clock. We're going to make ticks on a clock go forward, depending on what we're allocating. And as we move that clock in and we get to a certain level, then we'll evict the plan from cache. So you can go on this clock system and see, has my plan been part of the movement of a clock, and is it a candidate to be evicted from cache? Why does it matter if it's evicted from cache? You have to recompile the query to bring it back into cache. We have limits on the cache. We have caps, overall cap limits. We have limits based on the size and type and number of entries. I call this problem cache wars, because we'll get into scenarios where we hit our limits because of other things running in the system. The internal clock in, which is another column in these DMVs for your plan, will show, have you hit that clock? So you've got an external clock and an internal clock, both potentially moving, and either one of those clock hands hits a certain number, we have a candidate here to evict the plan from cache. We don't evict it immediately in these clock scenarios. It takes a certain number of ticks on the clock to decide, oh, we've had enough passes here that maybe this plan needs to be evicted. There are some forced scenarios that will cause plan cache eviction, and the clock hands aren't affected. It just evicts it. DBCC FreePOC cache or other flavors of that, which you can do per database. There are some altered database scope configuration options like procedure cache here you can do to clear it that does that. And here's the kicker. There are some SP configure options which are documented that when you run them, we clear the entire procedure cache or plan cache. That could cause you a performance problem. Pay close attention to those in production. You may want to run those only in an off production scenario. And then finally, I've had some people get into this and troubleshoot these kind of type problems. And then I ask them, are you being smart with what you cache? So for example, if you've got a lot of ad hoc plans being cached, maybe you should be parameterizing or using store procedures and if more efficiently use your cache versus worrying about what is getting evicted from cache. Okay, let's flip for a second here and talk a little bit about Linux containers and Kubernetes and Azure SQL. So first of all, the SQL Server engine is the same engine on Windows running on Linux. The difference is we use a piece of code called the SQL PAL as a layer to translate what we're doing in Windows in the SQL engine to Linux. So here's the difference. We have something called memory limit MB that we control, which is the maximum possible memory that SQL can see. So remember the targets I was talking about? Let's say max server memory was 0. And again, that 95% of physical RAM, well, in this case, memory limit MB is actually 80% of physical. So it's a little bit of a lower value that you would normally see on Windows. We do that because we want to avoid something called an out-of-memory killer. So Linux can page to the swap file, which it's just like their paging file. But what is more serious is sometimes the operating system can kill and terminate the SQL process if it is the highest memory user and there's out of memory conditions. This is why we default to 80% of physical, but you can change that. Notice here that locked pages are not applicable in this scenario. We do not have that concept called working set trims. Linux has a different behavior as we just talked about here. And there are kernel tuning best practices that we document that you should take a look at very carefully to ensure you do not run into these kind of problems. This memory limit MB is something you can adjust in something we call MS SQL conf. There are commands for you to be able to go and change this value. And in our benchmarks, we up this value a lot higher, and we get to a level we think that we can behave properly without running to these out of memory killer scenarios. Okay, what about containers? Okay, containers are just SQL processes running in an isolated way. All right. So if you try to mess with container limits from a container level, be very careful here. All right. I would prefer that you actually use memory limit MB and SQL Server memory to control memory, but it is possible to go control memory at a container level. And containers get default to all the memory on the system. This is not like each container only has a certain amount of memory unless you limit it with container engine, like Docker commands, for example, to do that. So think of it like a multi-instance scenario. So what I recommend you do, because these containers don't know about each other, right, is that you treat this containers of multiple ones running in a VM or bare metal like a multi-instance scenario, and treat it just like on Windows, where you would configure max and min server memories, or maybe even memory limit MB, to make sure these play nice with each other, or to prioritize the memory that you want. And finally, on Kubernetes, this is an interesting one. A huge call out to Anthony Nocentino, great friend of mine who knows a lot about Kubernetes. He was the one that brought his attention to me. I hadn't really played with this as much, and he showed it to me. So you have something called nodes in Kubernetes, and they have eviction policies where they'll actually, depending on the amount of memory that you're consuming, they'll actually terminate your pod and maybe potentially throw it onto another node, or even restart your pod, or even just evict the pod altogether. And those eviction policies are not something that SQL Server knows about. So make sure you have the right amount of memory allocated for a node in Kubernetes to support the amount of memory you need for SQL Server. And remember, in this environment, SQL Server and Kubernetes are SQL Server Linux containers. So you have memory limit MB to your disposal. That's what I recommended to Anthony that he consider also using as a way to control this. And you have max server memory as well for the SQL Server engine. Okay, what about Azure SQL? And when I talk about Azure SQL, I specifically mean SQL Server running in a PaaS environment, Azure SQL database and managed instance. So first of all, Azure Virtual Machine, sorry, I forgot that I had this on here. I just want to be clear about this. Azure Virtual Machine is the same as SQL Server. It is SQL Server running in a guest VM. It's just like running in VMware or in your environment with Hyper-V. But notice this, we have memory optimized sizes here. So you have the ability to choose how big you want your VMs based on your choice of Azure Virtual Machines, whether it's running on Linux, Windows, doesn't really matter. But inside the VM, configure SQL Server just like it is SQL Server. For managed instance, this is a little different. It's a managed scenario, right? So we limit memory per vCore, and it's a scale. It's a fixed memory scale with each vCore you add. The in-memory LTP feature is only available in business critical service tiers, and we enforce these limits with something called the Windows job object running in Azure. It's not a scheduling thing, it's a resource limitation thing. So a managed instance, depending when you choose general purpose or business critical, and your vCore option determines what is the maximum memory that SQL is possible to use. So think of this as like your physical memory limit that you would specify in your VM with MI. So you make a deployment choice, it gives you that ceiling of physical memory that SQL even has access to. For Azure Database, it's slightly different. It's a scaled memory limit, okay? So depending on the number of vCores you have on which service tier, the more vCores you go, the more memory you kind of get, right? And these limits are also enforced with job objects. You may not be aware of this, but on the M series choice, you have an M series choice of hardware choice for business critical. You get up to 4 terabytes of memory for your Azure database. Again, in-memory LTP is only a business critical. And then we have something called min and max for serverless. Serverless is like a range of memory because you have a range of cores you're using. You got a similar scenario with a range of memory. And it's possible that if we pause your serverless database, we may actually evict memory that you've allocated for SQL, and we have to go repopulate or rewarm that cache when it is resumed. Hyperscale has the same limits as general purpose, but don't forget that architecture has caches. A resilient buffer pool extension exists as an SSD drive to extend the cache of SQL Server on your computes, which effectively really extends the amount of memory you get with hyperscale. Okay, let's go just briefly look at some examples of this. I've got over here a VM that's connected to Azure SQL database. And I just want to show you this over here. I've connected to a business critical. Here's a business critical edition. Here's a general purpose one. Here's a hyperscale one. And here's a serverless one. Now you may be asking yourself, you're like, I don't know what my limits are. So first of all, you should know, let me flip over to here. Let me go back over here. In the documentation, and I've got this doc page up here, if I can find it. Yeah, here's a documentation talking about resource limits for Azure databases. And notice I choose my service tier over here. So let's pick general purpose provision compute for Gen 5, which is the latest hardware. And over here, I can say, hey, for general purpose with 8 cores, I get 41.2 gig of memory. That's my max memory limit that I'm providing. Notice here, you see the scaling. I go to 10, I get this. I go to 14, I get this, et cetera, et cetera. So if you go back over here and look at the actual VM, let's go back and do that. This is running, this is a business critical, but it's a similar concept. If I first run this DMV, I can go to this column and see that 42 meg number right here. Here is the limit. So you can go in and run a DMV to see without looking at the documentation, what is my limit? And again, let's be clear about this. This is effectively your ceiling. SQL automatically manages memory with maximum memory for Azure SQL database. You don't set that. So we will use that as the ceiling of what we can grow to. And we will have pressure. If there's pressure that occurs in the box, we will respond to that, but it's a managed service. So here's one of the great benefits of using Azure. We try to make sure there is no pressure on these machines. We try to make sure that ceiling is allowable at all times. And the way we enforce that is something called DMOS job object. And you can see with memory limit MB, notice here, that is the limit that we have for our business critical option. And you still have clerks. You can still go run here and see here. This is interesting. Notice here, though, there's a lot of buffers that have been allocated for extended events in this environment, because behind the scenes, it's not a lot of memory. But we're allocating extended events buffers because we're doing monitoring of the environment here. That's some of the managed environment monitoring that's going on. We still have buffer pool, all the other standard clerks you might see. Now, what about this one? This is, let's go to hyperscale. Oops. Go down here. This is my hyperscale database I'm connected to. I'm going to run some of the same queries here. And let's see what I got. In this particular case for hyperscale, I've got 80 cores. So I've got 80 cores, so I expect a lot more memory here. If I go over here to max DB limit, you can see here, yeah, I got a lot more memory. In fact, can you see how much memory I've got for this system, for my database that I'm allowed? And I can go in job object and see again that same, that's what's interesting. Those job objects limiting it lower. Well, what the heck's going on with that? Well, as it turns out, that's one of the benefits of this. We have the resilient buffer pool that's going on here. So that is part of our system to be able to help you extend your cache in the hyperscale environment. What about serverless? That we talked about ranges here for serverless. What about that one? This is a serverless system. You can see that right here. So let's look at that. And remember, I talked about these ranges. Now, notice here real quick on serverless that my mouse has gone like dead. Do you know why? It's because since the last time I used this, we paused it. It's been idle for a while. So it's trying to reconnect. Notice it says SMS is busy. This is because I'm trying to reconnect to that serverless database and get its cache warmed again so that I can reuse it. And this will come live here in a second. And I think I actually have some examples here, but you can see here it goes. You can see in serverless here, it's still going to show you that I've got 8 core limits, but it really is a range from 1 to 8. So this is still running. So when it comes back here, you'll see this range of 1 to 8, and you'll see the fact that our memory limits kind of reflect that. Should have come back here. It's still trying to come back, maybe. There we go. So I can see here that I have an 8 CPU because that's my max range. But if I look here at my max DB memory size, yeah, okay, so here it is. So I see my max DB memory size here, but then you're going to see here under job object, it's going to be a little bit lower than that. Yeah, notice here that the memory limit's lower. That's because we have this range of memory we're supporting with serverless. And again, you still see the same clerks that you see with any of the databases. This is showing you it's the same clerking system. It's the same engine running SQL Server. Here's the difference. The difference is that we have things we're controlling behind the scenes to enforce resource limits like job objects against the core SQL engine. If you yourself could go build a Windows job object in your own Windows system and enforce these same limits on the SQL process, we just happen to take advantage of that technology to do that. Okay. Wow. I hope that was kind of somewhat brain melting. Think about what I covered. I covered targets, totals, dynamic memory management. I covered ceilings. I covered locked pages, SQL lock, Windows lock. I showed you different APIs that SQL uses to manage this. I showed the architecture, the different caches. We talked about plan cache eviction, memory grants, Linux memory, container memory, Azure SQL memory, about everything you need to know about memory with SQL. And I hope what I've done is I've actually unblocked you from learning some of the nuances of why we do certain things and why we manage memory for you. Here are some resources for you. Remember, I told you that the deck is here. The demos are all available here for you to run. There's instructions on how to do that. Quick, again, reminder, do not use the Windows debugger in production unless guided by a professional like somebody from support from Microsoft or even somebody like myself. And I've got some other articles. When you get this deck, you can see here's some memory architectures in our documentation. Here's some articles that the CSS team has put together. Really good stuff about recommendations for max server memory and doing some of those configuration settings. When should you use large pages and not use large pages? Some of that is in there as well as some information about Azure to go get our Azure SQL training with the free sandbox and our SQL workshops was just a plethora of information. And then some guy wrote a bunch of books. Memory shows up in about every scenario here. So for example, in the SQL Server Linux book, I go into a very detailed description of how the PAL works and how we do memory management with the PAL. SQL 19 and Azure SQL Revealed also reveal certain memory internals that are specific to new capabilities with SQL or about how we do some of the limits that I talked about here today with Azure. This has been a crazy journey. I'm going to leave this slide up here and I'm going to stop. I've got about 8 minutes left here. So I just want to pause and see if there are any questions that you have about what we talked about. Anything about the memory of SQL or just general comments about whether you found this session helpful, somewhat brain melting, a lot of brain melting, or even maybe you found it too basic. And of course, if you found it too basic, we need to hire you probably at Microsoft. So, but anyways, hey guys, the data platform guys on the phone, let's see if they have any other questions here in the last few minutes that we have together.
Yes, Bob, there are some questions. So let me just call out the first question. I think you have already answered this, but when we should not use locked pages in memory, this is from Chinappan.
Yeah, I think I kind of addressed that a little bit when I stopped in one of the demos. I just got to be candid with you. Unless you're having a problem with it, I would always use it. Now, remember, it doesn't apply to Linux. You wouldn't be using it there. But for Windows scenarios, I would always use locked pages. The only thing that I would keep in mind is we have found, and customers have found, our top customers have found, big enterprise customers have found, that they usually set max server memory to something lower than physical memory. They don't set it to 0 in those cases, use locked pages. I'm not suggesting that that's by design or you have to do that. That's just a best practice we've seen. The problem is we can't tell you what the right number is to set it to less than physical memory. It's almost one of those trade-offs. Set it to a certain number less than physical memory, monitor your system and see whether you can grow even a little bit further and then kind of adjust it up as necessary. The article I show here on the screen that's in my deck, the CSS article, it references some suggestions about how you can do that.
Okay, Bob, next question is from Ahmed. Can we pin code into RAM? That is some essential query plan that I really don't want to be swapped out.
Yeah, unfortunately, there's nothing specific in there to do that. Plan cache eviction, the only thing you can do, in my personal opinion, there's no command to say, I'm going to run the SQL option and that particular plan will never get evicted from cache. The best thing you can do is to make sure you're using plan cache efficiently and that you're avoiding these other we believe that we have built SQL Server that your most important queries will stay in cache, okay? We think we've done that. The problems that people run into is when they have a lot of ad hoc queries that populate the cache, that floods the cache, right? Or some other problem occurs that's like a pressure problem that causes us to evict plan cache, or you run some sort of configuration command. So usually I haven't seen customers have a problem with this if they're efficient using plan cache itself and they're avoiding these pressure scenarios that cause us to evict these things from cache.
Thanks, Bob. Next question is from Robert Pearl. On the previous question about when not to use LPIM, what about when SQL Server sits on a VM host? Does that change the answer? Because you can lock memory for the VM as well.
Well, thank you for asking that question. It doesn't change the answer for Windows operating systems. And here's why. Inside the VM is running the Windows operating system, right? So I think I just showed you an example. If you inside the Windows operating system are not using locked pages, Windows can choose anytime it wants to trim your working set. We have seen scenarios where Windows will do this, even though there's plenty of physical memory on the system. That happens, right? And when you do that, remember what I told you, when a working set trim occurs inside that VM, when you do that, then SQL still thinks it's in RAM. And it is one of the most disastrous performance problems you can run into because we are not going to adjust anything. Now, having said that, there is one little caveat. We added code several releases ago that if we detect there is working set trim going on and 50% of the SQL Server working set has been paged out, we will start inducing pressure within our own system and start backing off our memory allocation. That's still a bad performance problem though, right? So yeah, in a virtualized system, the host doesn't matter here. It's what goes on inside the VM that matters the most. So when you do those operations you just talked about, it does not reflect on what Windows does inside the VM itself.
Right. Marcelo's question. Hi, Bob.
Hey.
LPIM affect a virtual machine failover, for example? Not necessarily sure this is a reason not to use it though.
You're talking about for large pages?
Yes, LPIM affect a virtual machine failover, for example.
Well, LPIM is locked pages in memory, not large pages. So let's distinguish the two, right? Locked pages, use it. I just don't know a reason why you wouldn't. I can't think of any scenario why you just wouldn't do this, right? Assuming you set max over memory. Large pages is different. Large pages is using these trace flags where when we start up SQL, we allocate all this memory up front. Okay, so first of all, startup takes a long time to do that. Second of all, there is certain behaviors of large pages with like column store you need to use a different trace flag for, or you're going to run into some issues. Here's my point. We do not believe that large pages is going to benefit most workloads. We put that in there because we know some workloads could benefit from it in some cases. If you go look at our TPCH benchmarks, they use it because they're maximizing every resource they can to get as much performance they can out of the system they're running on. But I just don't have a lot of customers out there that I believe should just by default throw on large pages. Go test for it for sure. Here's a little caveat. When we allocate large pages, we have to do it in these contiguous chunks of memory. I've seen scenarios where you don't get to even allocate all the memory in your system because we can't do it continuously within the operating system. So just be really careful with large pages, test it, experiment with it. Do not, in my personal opinion, put it on production blindly without going through that process. But lock pages in memory, Bob Ward at Microsoft.com, send me your example where that just was a bad idea because I just don't know why you wouldn't do it.
Sure, Bob. Next question, I think that's the last one from Yasir.
Okay.
At one counter or value that directly indicates my SQL Server needs more physical memory.
Let's see, your SQL Server needs more physical memory. You could say page life expectancy is one you could look at. I just don't do that because there's more to it than just buffer pool. I would go back to my total and target memory that I showed you, right? So if I find that my total memory is all the way to my ceiling, all the way and always there, it's just always sitting there, right? All the time, then maybe you do need some more physical memory. But here's the problem. It's too complicated of a situation because if I said that's the only thing you should look at, then somebody may come along and look at your system and say, oh, well, your queries are inefficient. You're just scanning all these tables when maybe you should have more efficient use of your buffer pool. And therefore, you know, just because you're hitting that ceiling doesn't mean you should just brute force add more RAM to your system, right? So I would just say, I look at total and target. Page life expectancy is not a bad thing to look at because of the fact that it does indicate in many cases what's the chance of these pages being found in cache. But I want you to think about one important point here. unless you have enough memory to cover your whole database, like what would be the limit you would ever pick, right? I mean, most people don't go buy hardware that covers the entire size of several databases they've installed, right? They get efficient in how they use what's cached, which is kind of what we did in hyperscale. If you think about that, we had to support hundreds of terabytes of databases, and we're not going to go out there and allow people to go build these replicas that have 100 terabytes of RAM. So we use resilient buffer pool extensions within our environment. We use these caches on SSD drives to kind of extend the buffer pool so that we can get a lot more smarter with it. Well, I just want to say a big thank you for everybody joining today. I hope you felt somewhat confused, somewhat brain melted, but then enlightened about some things you didn't know about how memory works. And hopefully this is going to help you going forward to make your SQL Server journey successful. I wish you all the best. Thanks again for being part of this event. Thank you to the organizers. I love being a part of it. And I bid everybody farewell, whatever time zone you are in. Have a great, blessed rest of the day.